Hello, my name is Tommie Kerssies, and in this video I will present our work on neural architecture search for visual anomaly segmentation. Industrial production lines are not perfect. Defective products need to be detected, and computer vision algorithms automate industrial quality control. And ideally, defective regions are segmented with pixel-level precision. This is the task of visual anomaly segmentation. The conventional approach to anomaly segmentation is supervised learning. We collect a large dataset of normal examples, also a large dataset of anomalous examples. We label the anomalous regions, and we train a model to segment those anomalous regions. However, in practice, it can be challenging to collect sufficient anomalous examples. Now, anomalies constitute rare events that deviate markedly from normal patterns. Anomalies can thus be segmented by identifying image regions with low probability under a probabilistic model of normal data. And this is the idea behind unsupervised anomaly segmentation, which only needs normal examples. A simple but effective approach to unsupervised anomaly segmentation is nearest neighbor scoring. In nearest neighbor scoring, we use a model encoder pre-trained on ImageNet, and we keep it frozen, unlike in normal training, which involves learning by updating model parameters with backpropagation. We extract feature patches from normal training images, and we store these in a memory bank. During inference, we compute the distance of the inference patches to the training patches, and we return a distance map indicating how anomalous each patch is. The state-of-the-art for unsupervised anomaly segmentation on the MVTech dataset is PatchScore. PatchScore relies on nearest neighbor scoring. It combines the output patches from multiple mid-level layers of the encoder. It increases the spatial awareness of these patches by using local neighborhood aggregation, which comes down to average pooling with a certain kernel size, which they call a patch size. And finally, they reduce the memory bank to a core set to increase inference time. In industrial quality control, the inference time of a model is vitally important to maintain a high throughput of the production line. Neural architecture search aims to search for an architecture that has as high performance as possible with as low computational complexity as possible. We aim to find the Pareto-optimal neural architectures. However, this is challenging because we only have access to a few anomalous examples. The research question therefore states to what extent the Pareto-optimal neural architectures can be approximated given a limited set of anomalies. The authors of PatchScore evaluate their method's performance using the area under the receiver operating characteristic curve. However, this metric has a problem under imbalanced data. 2.7% of the pixels in the test set of MVTech are labeled as anomalous. Therefore, only thresholds yielding a relatively low false positive rate on this curve will lead to meaningful segmentations. As you can see on the right, if we put the threshold above 10%, parts of the image will be segmented as anomalous, which are not. Therefore, this metric may not give a good indication of performance and would not be a suitable metric to be used as an objective value in a neural architecture search. Specifically for the case of imbalanced data, the average precision metric should give a better indication of performance because it circumvents the need for a careful selection of false positive rate limit because it's not using the false positive rate in its calculation. However, the average precision does by default not give equal importance to different sized anomaly regions or different anomaly types with different numbers of regions if we're doing it purely on a pixel by pixel basis. Therefore, for the specific task of visual anomaly segmentation, we introduce in this work the region-weighted average precision. Now we have established a metric for measuring the performance of a certain architecture. We need a search space of different potential architectures to search in. A common approach is to use a supernet, which is designed consisting of multiple subnets that share weights. The supernet is trained only once, allowing for the extraction of specialized subnetworks that can be deployed under different domains, tasks, hardware, and latency constraints. This approach to neural architecture search significantly reduces the search cost and computational resources required to find optimal architectures compared to doing neural architecture search methods that train each candidate architecture independently. Now, nearest neighbor scoring is very well suited to neural architecture search, is what we find in this work, because subnets from a pre-trained supernet can directly be used as encoder without any additional training. We find that larger frozen pre-trained encoders do not necessarily lead to better performance for anomaly segmentation, and smaller encoders may do just as well. Therefore, we introduce a search space based on the very lightweight MobileNet v3 architecture. And this supernet is pre-trained on ImageNet by Vanschoren and is directly used to search in without any additional training. Now, similarly to most convolutional architectures, the number of feature maps increases sequentially, while the resolution of the feature maps decreases sequentially. And for each stage, the expansion ratio and kernel size for the blocks in that stage are searched. Furthermore, we search for the blocks to extract from and the kernel size for average pooling, the local neighborhood aggregation. To automate the search process, we represent it as a multi-objective black box optimization problem. The multivariate multi-objective tree parsing estimator is an effective algorithm to address this problem. In an iterative manner, the algorithm proposes an architecture from the search space. The anomaly segmentation process first populates the memory bank with patches from normal images in the training set and subsequently predicts anomaly scores for patches from normal and a few anomalous images in a validation set. With ground truth masks of these few anomalous regions and the predicted scores, the region-weighted average precision is calculated and returned along with the flops of the architecture as the objective values to the algorithm, after which the algorithm proposes a different architecture and the process repeats. After performing this iterative search process for a specified number of trials, the Pareto optimal trials are identified as those that cannot be improved in one objective without deteriorating the other. With just one example per type of anomaly, the AUTOPatch method shows more refined segmentation than the current state-of-the-art patch score, as can be seen in the following qualitative examples. This example shows a false negative for patch score, however, a true positive for AUTOPatch. The results of searching using the aforementioned method are shown in this slide. The results of the architectures with the highest performance are presented. Patch score results are included as a baseline on the left and using all anomalies for searching as an oracle on the right. All reported values are the region-weighted average precision in percentage on the test set, and the G-flops are in parentheses. AUTOPatch outperforms patch score for 13 out of 15 categories with only one example per type of anomaly, while the architectures discovered by AUTOPatch require significantly fewer flops compared to the default white resonate 50 that is used in patch score. Increasing the number of anomalies used for the search improves the performance to some extent with diminishing returns. The following figure shows the Pareto optimal architectures. On the x-axis, we plot the computational complexity, and on the y-axis, the region-weighted average precision on the test set. The orange dots represent the architectures found by using the small validation set, and the blue dots represent the architectures found using the test set itself as an oracle of how good of a Pareto front we may expect to achieve. Now, as you can see, in certain cases, the blue dots are very well approximated by the orange dots. However, in some cases, such as for the carpet on the top right, the highest flops architecture is actually one of the worst performing architectures, and these outliers are one of the limitations of our work. In conclusion, we found that with only one anomalous example per type of anomaly, AUTOPatch outperforms the prior work on the MVTech dataset with significantly fewer computational resources. Now, most categories, they show a close approximation of the Pareto front, with 1 or 2 anomalous examples per type of anomaly. However, the effectiveness depends on the specific anomalies available, and we see that they can exhibit considerable variance in real-world performance in certain cases.